Hello, welcome to this video series where we are going to talk about industrial machine control. From fundamental concepts over standards to some advanced topics, we will cover different viewpoints of the machine control, from electrical principles over control techniques to software and IT engineering. When we think about machine control, the first question that comes to mind is, what can we actually control to control a moving part or a process on a machine? To answer this question, we should remember that actually a movement or a process is a work produced by an energy. So, to control a movement or a process, we need to control the energy flow to that actuator that transforms the energy into movement or a process. The next question that comes to mind is, what kind of energy is typically used to drive an industrial machine? And the answer is, there are three forms of energy used for this purpose. First, the electrical energy, which drives, among others, electrical motors, and which is controlled by relays or drives. The second form of energy is the pneumatic energy, which drives, among others, cylinders, and which is controlled by open and close valves. And the last energy form is the hydraulic energy, which is less used nowadays. In fact, the electrical energy is the most important one, because it is always present in any modern industrial machine. The secret lies in the fact that the electrical energy is used in two ways: to control the movements and process, and to drive them or some of them. To drive heavy loads, a high voltage for the power circuit is needed, whereas to control or to power small devices, a low voltage for the control circuit is enough and safer to use. Now let us examine a typical main supply current cascade of a simple industrial machine as in the wiring diagram. We first notice the cabinet lighting and socket, usually protected by some fuses. These are connected before the main switch, so that even if the latter is turned off, one can still use them to do some electrical work on the cabinet. After that, we can see the three-phase main protection with the machine nominal current. After that point, the circuit can be split in two main voltages used throughout the machine: the three-phase power voltage that is used for heavy duty, and the DC 24-volt circuit, derived by a converter which powers all control devices on the machine. The power circuit is all about delivering the raw electrical energy to the components that actually do the work. It is the heavy-duty part of the electrical system. Its purpose is to supply high voltage and current to operate loads that require significant power, such as motors, heaters, lights, and alike. Some of the power circuit components are the power source, which is the main incoming electrical supply, like the utility grid, a generator, or battery bank. It also includes the circuit breakers and fuses, which are overcurrent protection devices that protect the circuit from damage due to overloads or short circuits. Contactors or motor starters, which are electrically operated switches that connect or disconnect power to large loads like motors, which are also part of the power circuit. And by the way, these are the most common load in a power circuit, converting electrical energy into mechanical motion. There might also be some heaters which convert electrical energy into heat for some heating or drying process. Also, power transformers that are used to step up or step down voltage levels for different power requirements are part of the power circuit. Finally, we don't forget the heavy gauge wiring, which are used to safely carry the high currents without overheating. What we should bear in mind about the power circuit are the following aspects. First, it typically operates at higher voltages such as 240 volts, 400 volts, 600 volts AC, and higher currents. Second, it is therefore designed to handle significant power, watts or kilowatts. Third, it focuses on energy transfer and the physical work being done. And the last aspect is about the safety of the power circuit, which is obviously paramount due to the high energy levels. The control circuit is where the intelligence and decision-making happen. It's responsible for telling the power circuit what to do and when to do it, usually with much lower power levels. Its purpose is to manage, monitor, and automate the operation of the power circuit and the overall machine. It works on cyclic manner, which consists of 3 steps: take inputs, processes them, and then sends commands to the power components. The control circuit is composed of, first, the control power source, which is often a lower voltage power supply, like 24 volts DC, derived from the main power source via a control transformer. This isolates the control circuit from the higher power circuit as seen previously. Second, the input devices like push buttons and switches that are manual operators for starting, stopping, or selecting modes. Limit switches used to detect the physical position of machine parts. Proximity sensors used to detect the presence of objects without physical contact. Photoelectric sensors used to detect objects using light beams. Temperature and pressure sensors used to monitor environmental or process conditions. Third group of components are the logic devices, such as programmable logical controllers, known as PLCs, which are the most common brain in modern industrial machines, executing programmed logic. Relays, that are electrically operated switches that use a small control current to switch a larger current, often used to interface between control and power circuits. Timers and counters, which provide time-based or count-based control used in simple logic control. The control circuit includes also the output devices that are actuators for the control circuit, are typically indicator lights and buzzers, which provide visual or audible feedback to operators. Solenoids, that electrically activate valves or small mechanical devices. Control relays, which are used to switch other control circuits or to provide an interface to contactors in the power circuit. What we need to keep in mind about the control circuit is, first, it typically operates at lower voltages, like 24 volts DC or 120 volts AC, and lower currents. Second, it handles information, logic, and signaling. Its role is the automation, sequencing, safety interlocks, and operator interface. And finally, it often uses smaller gauge wiring because of the low power involved. To make this working principle clearer, let's have a look at a simple motor starting action example. At the control circuit level, following steps take place. First, the operator presses the start push button, which is a PLC input. At the same time, a limit switch detects that the safety guard is closed, which is also a PLC input. The PLC, which is the control logic device, reads these inputs. The PLC's program checks that both conditions are met, and the PLC sends a low voltage signal to a control relay through one of its digital outputs. The control relay in turn energizes, closing its contacts. The control relay is in this case the interface between the two circuits because its contacts are wired into the coil of a motor contactor in the power circuit. At the power circuit level, following happens. When the control relay contacts close, they complete the low voltage circuit to the motor contactor's coil. In turn, the motor contactor's coil energizes, causing its main power contacts to close. This connects the high voltage, high current power directly from the main power source to the motor, and this leads the motor to start running. Now that we have seen both the control and the power circuit, let's see how the control circuit enables or disables the power circuit. Well, beside the safety control, which acts in a similar way, there are usually 2 buttons on industrial machines that fulfill this function, often labeled Control On and Control Off. These are operator push buttons that command the machine's control system to enable or disable the machine's control logic and, often also the main control power to actuators. They are part of the control circuit, low voltage logic, and they interact with the safety circuits and interlocks. The typical way how control-on works is control-on latches the control circuit on via a holding circuit, enabling PLC logic to run the machine. Control-on may energize a control relay or contactor, such as a control relay, CR, or a master control relay, MCR, that supplies power to field inputs-outputs. Pilot devices and solenoid outputs. Control-on often checks permissions first, emergency stop released, guards closed, air and hydraulics up, and no fault signal. The typical way of control-off works is control-off unlatches the control circuit, de-energizing the same relay or contactor and disabling outputs. Control-off provides a controlled stop of the machine's logic side. It's not a substitute for an emergency stop. Control-off often drops the MCR zone so that outputs to actuators are de-energized. To better understand the previous explanations, let's have a look at the simplified common wiring pattern of the power on and power off buttons, which looks like a power supply of 24 volts DC, which represents the control supply, is led through a series of contactors made by, first, a normally open control-on light button, which is connected in parallel with relay normally open contactor for seal-in. Second, an emergency stop contactor that is normally open. Then comes also some guard interlock contactor that is also a normally open contactor and which is also safety rated. The last contactor is the control off button, which is a normally closed one. These in serial connected contactors allow energizing the coil of the master control relay, MCR, with the 24 volts. The MCR's auxiliary power contacts then provide plus 24 volts DC to the following groups. The PLC output commons feeding solenoids and relays, as well as the contactor's auxiliary control, and also any pilot devices as needed. Last, we should know that the control chain to the MCR is usually hardwired so loss of logic, a PLC level, cannot leave actuators energized. Even though usually, the buttons are also read as PLC inputs, so the PLC knows the operator pressed a on or off button. To summarize, one can keep in mind following three important conclusions. First, the power circuit and the control circuit in a machine are like the muscle and the brain of an operation, working together to make things happen safely and effectively. Secondly, that the control system of an industrial machine runs an eternal cycle consisting of reading inputs, processing them, and sending commands to the power components. And for last, the power voltage can be turned off using either an emergency stop or other safety device, but also using the control off button, although these two work differently, especially that the latter cannot replace the emergency stop or any other safety device. In future, there might be some videos about industrial machine safety from the control point of view. With all this said, thanks for watching. I hope you enjoyed the video. If so, please like, leave a comment, and subscribe for more videos like this one.